Imagine looking up at a towering bridge or maybe walking through a really modern high-rise building. We rely on these structures, every single day. But beneath the surface, time and wear, they're constant forces. So how do we keep our vital infrastructure safe and strong and functional for decades? It's not just some hypothetical question. It's a huge engineering challenge, and it drives constant innovation. Today, we're taking a deep dive into one such innovation: bubble deck slabs. It's a fascinating, really lightweight concrete technology. Our mission here is to unpack a really insightful new study. It's by M. Bader and colleagues, just published this year in Fracture and Structural Integrity. This paper tackles a critical question, really, for the future of buildings using this tech. How effectively can damaged bubble deck slabs be strengthened using this remarkable material called carbon fiber reinforced polymer, or CFRP sheets? So we're going to try and understand the clever design behind these slabs, the specific challenges they face, and then explore the surprising impact of things like the internal void size and, pre-existing damage on how well they can actually be repaired. Okay, so let's unpack this a bit. What exactly are bubble deck slabs?
Well, think of a standard reinforced concrete slab, right? But with a clever twist. They embed these hollow, porous plastic spheres right into the core of the concrete.
Okay, plastic spheres inside the concrete.
Exactly. And it's not just for looks or anything. This design significantly cuts down the amount of concrete you need. And critically, the overall weight of the slab itself.
Ah, so lighter structures.
Precisely. And the advantages are pretty compelling. Less concrete means they're, potentially more environmentally friendly, definitely more economical in terms of materials. And being lighter reduces the load on the foundations below.
Makes sense.
Plus, the air trapped in those voids acts a bit like insulation, which can help with the building's energy efficiency. And because they're often made as modular units, they can even speed up construction time on site.
It sounds like a really ingenious solution for reducing weight.
It truly is. But, like with any innovation, there are trade-offs. While they're fantastic for saving material, these slabs face particular challenges, especially with what engineers call striking shear strength.
Striking shear. What's that exactly?
It's essentially how well they resist a concentrated, sort of punching-like force. Think of maybe something heavy dropping in just one small area.
Okay, like an impact load.
Right. And crucially, rehabilitating them once they're damaged can be complex. This challenge becomes particularly pronounced in what we call two-way slabs.
Two-way.
Meaning the load doesn't just transfer in one direction like in a simple beam, it spreads out across the entire surface in two directions. So any weakness in one spot can more easily affect the whole structure. It gets intricate.
That's a fascinating challenge. So if these lightweight wonders do get damaged, how do engineers go about fixing them effectively? This is where carbon fiber reinforced polymer, or CFRP, comes into the picture, right? As a promising solution.
Exactly.
We've actually touched on CFRP before in these deep dives. It's an incredible material, known for its extremely high strength-to-weight ratio, its impressive resistance to corrosion,
Which is huge.
and it's relatively easy to install compared to, say, adding more steel or concrete.
Absolutely. It's commonly used to reinforce conventional concrete structures, standard solid slabs, beams, columns.
Right.
And this is precisely where the Bader study really shines a light. What's so important here is that despite CFRP's proven track record on solid concrete, there's been a significant gap in our understanding, a real dearth of research, as they say, specifically on applying it to bubble deck systems.
Ah, because of the voids.
Yes. Engineers haven't really had a clear picture of how effective it is when those internal voids are present or how, varying levels of existing damage might influence the repair's success. This study is crucial because it systematically looks at how those specific factors, the size of the voids and the degree of pre-existing damage, influence how well CFRP can restore the structural performance. It's answering questions that, frankly, haven't really been addressed head-on before.
Okay, so how did the researchers actually put this to the test? It sounds like a complex problem to model accurately.
It really is. They designed a meticulous experimental program. It involved 9 distinct slab specimens.
9 slabs!
One was a solid control slab, just standard reinforced concrete. That gave him a baseline for comparison.
Made sense.
The other 8 were bubble slabs. They were created with plastic spheres of 2 specific diameters, 50 millimeters and 60 millimeters.
Okay, so 2 different bubble sizes.
Exactly. And to make sure they behave like actual building floors where loads spread out, they reinforced them with both top and bottom steel lattices. That ensures the critical two-way load transmission we talked about.
Got it. What about the materials themselves, the concrete, the steel?
Yeah, good question. The concrete they used had a specified compressive strength of 30 megapascals, pretty standard. And the steel reinforcing bars had a yield strength of 460 megapascals.
And the CFRP itself, what were its properties?
Right. The CFRP material was quite specific. They chose bidirectional sheets,
Bidirectional.
meaning the carbon fibers run in two perpendicular directions, 0 and 90 degrees. So it offers strength along both axes of the slab.
Okay.
Each sheet had a nominal thickness of just 0.167 millimeters.
Wow, that's incredibly thin.
It is. But don't let that fool you. It boasts an impressive tensile strength of 3,500 megapascals.
Huge pulling string.
Massive. And an elastic modulus of 230 gigapascals, which tells us it's incredibly stiff, it resists stretching. These sheets were then externally bonded to the bottom surface of the concrete slabs, essentially glued on.
Glued on, basically.
Using a specialized two-step epoxy system, they followed, well-established guidelines for these types of repairs to ensure a good bond.
So they didn't just test pristine slabs. You mentioned simulating real-world wear and tear. They actually damaged the slabs before applying the CFRP. How did they do that?
Precisely. This is key. To simulate realistic scenarios, the slabs were preloaded. They applied load up to specific percentages of their ultimate capacity. That's the maximum load they could theoretically take before failure, before any CFRP was applied.
Okay, what sort of percentages are we talking about?
They chose levels of 50%, 60%, and even 75% of that ultimate load.
75%. That sounds like a lot of damage.
It is. It was a really smart approach, actually.
And what was the thinking behind choosing those specific preloading levels? Why 50, 60, 75?
That's a great question. They were chosen very deliberately to simulate, as you said, realistic damage scenarios you might encounter in an actual structure. Think of it as a range from early stage, maybe minor cracking at 50%, all the way up to conditions very near failure at 75%.
Okay.
The 75% preloading level, well, that was considered the practical upper limit for effective CFRP rehabilitation. The concern is that beyond this point, the existing damage, the cracking in the concrete, might be so severe that the CFRP simply wouldn't bond properly.
The glue wouldn't stick well enough.
Exactly. It could compromise the whole repair. It's like trying to patch a hole that's already torn too wide. The patch won't hold.
Right, that makes sense. So once the damage was simulated, the CFRP was applied. How did they actually test these repaired slabs? What was the setup?
They put them through a pretty rigorous testing protocol. It involved monotonic central loading.
Monotonic, meaning?
Just slowly and steadily increasing a single force applied right to the center of the slab, pushing down. No cycling, just a steady push until failure.
Okay.
The slabs were supported along all four edges, which mimics how a real floor slab in a building would typically be supported.
Right.
They used a massive 200-ton universal testing machine, and they meticulously measured how much the slabs deflected or sagged under the load. They also observed how new crack patterns formed and spread. And ultimately, they identified the specific ways the slabs failed, what engineers call the failure modes.
Okay, let's dive into those fascinating findings then. Starting with the baseline. How did the unreinforced bubble slabs, the ones without CFRP, compare to the solid concrete control slab?
Yeah, this is where we start to see that inherent trade-off pretty clearly. The unreinforced 50-millimeter void slab, which they labeled SB50, it showed a 4.1% reduction in its ultimate load capacity compared to the solid slab.
Only 4% down. That's not too bad.
Not terrible, no. But interestingly, it had a 9.3% increase in deflection at that ultimate load.
Ah, so it sagged noticeably more.
Yes. Even though the load drop wasn't huge, the stiffness was affected.
So right off the bat, we're seeing that weight reduction comes with a performance hit, especially in stiffness.
Exactly. And the unreinforced 60-millimeter void slab, the SB60, it fared, well, a bit worse. It showed a more significant 13.5% reduction in ultimate load capacity.
Okay, that's a bigger drop.
And a 2.3% increase in deflection compared to the solid slab. Still sagged more, but the load capacity drop was the bigger story there.
So what does this all mean? It seems clear.
It's clear that the very presence of these voids inherently reduces a slab's ability to carry the maximum load, and it can increase how much it sags under load. And importantly, the bigger the void, the greater the reduction in performance, particularly load capacity. It's a direct consequence of having less concrete.
Okay, here's where it gets really interesting for me. What happened when they applied the CFRP to those 50-millimeter void slabs, the Group 1 specimens? Did it actually make a difference? Did it bring them back?
It made a significant difference, yes. After they applied the CFRP, their ultimate load capacity actually increased by somewhere between 1% and 4% compared to the original unreinforced bubble slab.
Increased, so stronger than before they were damaged.
Stronger than the undamaged bubble slab baseline, depending on the pre-damage level. And maybe even more impressively, the deflection at failure was reduced by up to 23%.
Wow. So not only did they regain strength, potentially exceeding the original bubble slab, but they also became much stiffer too, less sag.
Precisely. They became more rigid. For a specific example, take the 50 mm void slab that was pre-damaged to 50%, that specimen SB550. It recovered approximately 98.5% of the solid control slab's load capacity.
Almost back to the solid slab level.
Almost fully restored. And its deflection was reduced by around 22.5% compared to the unreinforced bubble slab. That 98.5% recovery isn't just a number. It really shows the potential of CFRP to almost fully restore a pre-damaged structure. That's a massive win for engineers looking to extend the life of these slabs.
That's incredible. What about the one damaged to 75%?
Even the most severely pre-damaged 50 mm slab, the SB575, it still carried about 94.3% of the solid control slab's load.
Still over 94%.
And it reduced deflection by 25.5%. So even with heavy damage, the CFRP provided very strong recovery and significantly enhanced rigidity for the 50 mm void slabs.
That's quite impressive for the 50 mm voids. Now, what about the 60 mm void slabs, group 2, with the CFRP? Was the outcome similar, or did the larger voids present a different challenge for the repair?
The results for the 60 mm void slabs, well, they definitely told a different story, a bit more nuanced. While these also showed recovery, their ultimate load increased by 5% to 9% compared to their unreinforced state. The percentage of recovery relative to the solid control slab was generally lower, especially for the more severely damaged ones compared to the 50 mm group.
Okay, so the repair wasn't quite as effective overall.
Less effective in terms of reaching that solid slab benchmark, yes. And here's a key difference in stiffness. For instance, the SB660 specimen, that's 60 mm voids, 60% pre-damage, it actually exhibited a 12% increase in deflection despite the strengthening.
An increase in deflection, even with the CFRP.
Yes. So while it got stronger, it actually became less stiff. It sagged more than the undamaged 60 mm bubble slab. This indicates that stiffness recovery was somehow compromised at these higher damage levels when the larger voids were present.
That's counterintuitive.
It is. And the SB675 specimen, the most damaged 60 mm one, only retained about 82.5% of the control slab's load. Still an improvement over the unrepaired state, but significantly less recovery than the 50 mm equivalent.
So the repair was definitely less effective with the larger voids, particularly when combined with more severe pre-damage. And what did the researchers observe about how these strengthened slabs ultimately failed? Was it different between the groups?
This is critical for understanding where the weak link lies in the repaired system. The predominant failure mode observed across all the CFRP-strengthened specimens, both 50 mm and 60 mm, was debonding.
Debonding, the CFRP peeling off.
Exactly. The CFRP sheet separating from the concrete surface, often quite suddenly, and also flexural fracture, which is basically cracking or breaking of the concrete itself due to bending.
What didn't they see much of?
What they didn't see much of was that punching shear failure we talked about earlier, where a concentrated load punches a plug straight through the slab.
Ah, okay.
If we connect this to the bigger picture, it signifies that the bond interface, that connection between the CFRP and the concrete, not the concrete strength or the steel reinforcement itself, was the limiting factor. It determined the ultimate performance.
So the system failed at the glue line, essentially.
Right. The repair system was failing at its adhesion point, not necessarily the materials themselves breaking.
That's a fascinating insight. If the bond is the weakest link, does that suggest there's a limit to how much CFRP can actually achieve, regardless of the slab's initial damage level?
It absolutely does. It
Yeah.
means engineers need to pay extremely close attention to surface preparation before applying the CFRP and the epoxy bonding process itself. You need a clean, sound surface.
All right, the prep work is crucial.
Crucial. Even the strongest CFRP won't work if it can't stick properly. And yes, it suggests there's a practical limit to the load transfer capabilities of this kind of external CFRP bonding. It might push designers to think about alternative or maybe complementary strengthening techniques if you're dealing with very, very high loads or expecting extreme conditions.
So, considering all these findings, what are the big takeaways from this deep dive? For anyone involved in structural design or maintenance or rehabilitation, what should they be thinking about based on this study?
Okay, I think the most critical conclusion, unequivocally, is that the void size substantially impacts both the efficiency of retrofitting and the structure's overall performance after repair. The study starkly showed that difference. Unreinforced 50 mm void slabs kept 96.2% of the solid slab's strength, while the 60 mm voids only achieved 86.5%,
The 10% difference, roughly.
roughly, which strongly suggests that for new designs, using smaller voids, specifically 50 mm or perhaps even less, seems more suitable, particularly if you anticipate potential damage down the line or the need for future rehabilitation.
Plan for repairability from the start.
Exactly. It also highlights that sweet spot for CFRP intervention. Its effectiveness, its efficiency significantly decreases as the pre-damage increases. The study found CFRP was most effective when damage was restricted to that 50% to 60% of the ultimate load range.
So fix it sooner rather than later.
Absolutely. Early intervention is key for optimizing both the technical efficiency and the cost-effectiveness of the rehabilitation. Waiting until damage is severe makes the repair harder and less effective.
They also found something quite surprising you mentioned about serviceability, which is, a really important practical consideration for buildings, how they feel, not just how strong they are. Even with the CFRP applied, all the tested slabs surpassed the serviceability deflection limit,
That's right.
which for these slabs was an engineering standard of the span length divided by 240, or about 4.17 millimeters of sag. What does exceeding that limit actually mean for a building or its occupants?
This raises an important practical question. Exceeding serviceability deflection limits means that even though the floor is strong enough not to collapse, it might still sag more than building codes typically allow for comfort and function.
So it might feel bouncy when you walk on it?
It could lead to a feeling of bounciness, or visible sagging over time. Maybe even practical issues like partition walls cracking or doors sticking. It impacts the usability and perceived quality of the space.
Okay.
So it indicates that CFRP strengthening alone, while great for strength, may not be sufficient to ensure serviceability, especially in severely loaded slabs or perhaps ones with longer spans.
So what's the solution then?
Designers might need to consider a hybrid approach, maybe combining CFRP for strength with other techniques focused on stiffness, like internal prestressing.
Where you embed tension steel cables.
Exactly, to actively counteract sagging. Or perhaps adding supplementary supports like beams underneath, if feasible. It's about meeting all the performance criteria, not just ultimate strength.
Now, every good study has its limitations, right? And this one is no exception. A key point you mentioned was that only a single specimen was used for each test condition.
Correct.
While the results are definitely promising, that always means statistically they should be interpreted a bit cautiously, just due to the inherent variability you get with concrete structures.
That's a fair point, and it's important to acknowledge. Concrete isn't a perfectly uniform material like steel. Slight differences in mixing, casting, or curing can lead to minor variations in strength, even between nominally identical specimens.
Right.
However, the researchers did take significant measures to try and reduce that variability. Things like consistent casting and curing procedures for all slabs, and using precise instrumentation during testing.
So they controlled it as much as possible.
As much as practically possible in a lab setting. But yes, to establish full statistical significance and really confirm these observed enhancements in load capacity and deflection control across the board, future research would ideally involve larger sample sizes, more tests per condition. This study provides a vital foundation, though. It clearly shows the trends.
Absolutely. So for designers out there right now, maybe working on new construction projects using bubble deck slabs, what's the ultimate practical recommendation you'd pull from this research?
I'd say if long-term durability, serviceability, that stiffness aspect, and the potential need for future rehabilitation are high priorities for your project, then based on this evidence, a void diameter of 50 millimeters seems strongly recommended over 60 millimeter.
Go smaller on the voids if you can.
Yes. Designers should evaluate void size, not just as a geometric parameter to save weight, but as a critical factor that fundamentally impacts a structure's future repairability and its damage tolerance. How much damage it can sustain before it becomes unusable or hard to fix. It's a design choice with real ripple effects for the entire lifespan of the building. Think about the long game.
This deep dive has really illuminated the innovative nature of these bubble deck slabs, the remarkable power of CFRP as a strengthening material, and crucially, the often overlooked role that internal void size plays in a structure's future repairability and resilience. It's a testament, really, to how even seemingly small design choices can have pretty profound consequences down the road.
It's a fascinating look into a specialized area of engineering, for sure. But what stands out to me is how this principle kind of extends beyond just concrete slabs. It highlights a broader truth, I think, in engineering and maybe even life itself. That the initial design choices, the foundations you lay, even seemingly small ones like the size of a void or a minor decision early in a project, can have profound long-term implications. Implications for resilience, for the ability to adapt and recover from future challenges, whatever they may be. Thinking holistically right from the start is just so key.
I couldn't agree more. It really makes you consider what other, perhaps hidden design parameters might significantly impact long-term performance, maybe in your own areas of interest or work. So, a question for you listening. What stands out to you about how initial choices, maybe small ones, ripple into the future?